Okay, myself, I am Dr. Shankaraiah, Associate Professor in Department of Physics. So, in today's presentation, I am going to discuss about third module, lasers and fiber optics, in which I have discussed some topics in lasers. So, today, so we will discuss population inversion, metastable state, and lasing action. Okay. So, what is this population inversion, and what is metastable state, and what is the use of the metastable state, and why do we need this lasing action? Okay. So, we will discuss about all these three topics in this presentation. Okay. So, in population inversion condition, the population distribution between levels E1 and E2 is inverted, and hence it is known as inverted state. And this inverted state is a non-equilibrium state and exists only for a short time. Okay, so he is saying that population inversion condition, in population inversion. Okay, so to understand what is this population inversion, so I think I've discussed a little bit in the previous presentation, but okay, I'm going to revise some and then we'll discuss the next topic. So to understand this population inversion, I am considering two energy levels, E1 and E2. Okay, and E1 is a ground state. So E1 is a ground state, and we all know that ground state is the lowest energy state. So ground state is lowest energy state of a system, lowest energy state of a system. Okay, so ground state we are considering two energy levels E1 and E2 to understand the population inversion condition. Okay, so in this, E1 is the ground state. We know that ground state is the lowest energy state, and E2 is the excited state. E2 is excited state, and we know that E1 is E2 is greater than E1. So whenever we are saying ground state and excited state, so E1 is the ground state, that is the lowest energy level, and E2 is the excited state. So the energy of the excited state is always greater than the energy of the ground state, because ground state is the lowest energy level. So now we are saying that first, to understand this population inversion, first we need to understand something called normal state. Okay, so what is a normal state? Okay, here I am trying to understand what is a normal state. Okay, normal state. What happens in normal state? So normal state is nothing but equilibrium state. In equilibrium, we are going to see this normal state. In equilibrium, what happens is that all the atoms of a particular material will be in the ground state, lowest energy level, and there will be very few atoms in the excited state. Okay, so normal state is also called as equilibrium state. Equilibrium state. Normal state is also called equilibrium state, and here these open circles are nothing but the number of atoms, and here the number of atoms in ground state are denoted by N1. Okay, so I'm saying N1 is the number of atoms in the ground state, and N2 is number of atoms in the excited state. Okay, so number of atoms in the ground state, look at the number of atoms in the ground state. There are more number of atoms in the ground state compared to the number of atoms in the excited state. So here N1 is greater than N2. N1 is greater than N2. So more number of atoms are in the ground state, and there are very few atoms in the excited state. That is the reason why I am saying N1, which represents the number of atoms in the ground state, is greater than N2, which represents number of atoms in the excited state. So when N1 greater than N2, number of atoms in the ground state are more compared to the number of atoms in the excited state. So this state is called normal state, and this are also called as equilibrium state. Okay, so now we know what is a normal state or what is a equilibrium state. Now let us try to understand what is this non-equilibrium state or inverted state. Okay, Fine. So we understood one condition, which is n1 greater than n2, and we said this is normal state. Okay, normal state. Okay, very good. So in two conditions, yeah, E2 is greater than E1, that is fine. Excited state energy is always greater than the energy of the ground state, because the ground state is the lowest energy level of the system. Okay, so now n1 greater than n2 is a normal state or equilibrium state. Very good. So now we understood that. Now let us see what is inverted state. We know what is normal state. Let us see what is inverted state. Again, we are taking two energy levels, E1 and E2. Same. E1 is ground state and E2 is excited state as before. Okay. So ground state, E2 is excited state. Okay. Now, in this condition, now again I am representing number of atoms by open circle. So there are number of atoms in the ground state are very less, 1, 2, 3. Okay, so number of atoms in the ground state is represented or denoted by n1, and number of atoms in the excited state is denoted by n2. Okay, here it is clear that there are many atoms in the excited state, right? So n2 is greater than n1. N2 is greater than N1. So when there are many number of atoms in the excited state compared to the number of atoms in the ground state, this state is called as inverted state. And this is a non-equilibrium state, because in general in equilibrium we don't find all the atoms in the excited state. In the equilibrium state, all the atoms are going to sit in the ground state. So that is why we called it as normal state or a equilibrium state. But now this n1, n2 is greater than n1 is not a equilibrium state, because this kind of situation we will not see in equilibrium. This can occur only in non-equilibrium. Okay, so to achieve this non-equilibrium state or inverted state, we need to supply energy to the system so that the atoms in the ground state will go to the excited state. Okay, so that we will discuss later. But this state where n2 is greater than n1, N2, the number of atoms in the excited state are more compared to the number of atoms in the ground state. So this state is called inverted. This is not normal, this is inverted. Okay, this is inverted state. Also, this is also called as non-equilibrium state, because this we don't see generally this kind of situation in equilibrium. Okay, so now we know what is a normal state and what is a inverted state, or what is a equilibrium state, or what is the condition for equilibrium state or normal state. So the condition for normal state or equilibrium state is n1 greater than n2, where n1 is number of atoms in the energy level E1 and n2 is number of atoms in the energy level E2. Very good. Next, we also understood now another condition or another state which is called as inverted state, which is a non-equilibrium state. Here n2 is greater than n1. The number of atoms in the energy level E2, which is the excited state, are more compared to the number of atoms in the ground state. So this is inverted state, and this is also called as non-equilibrium state. Okay, to achieve this non-equilibrium state, we need to supply energy to the system so that we get this. Okay, now very good. So yeah, one more important point is that this non-equilibrium state exists only for a very short time. That means number of atoms in the excited state should be more compared to the number of atoms in the ground state. This kind of situation will not stay for a long time. In a short time, very short time, you will find the atoms in the excited state will decay to the ground state. So that is why this inverted state or non-equilibrium state exists only for a very short time. Okay. Whereas normal state exists for a quite more time compared to the inverted state. Okay. And what is the importance, or why do we need this? And this condition also very important. We have discussed that this is an inverted state or non-equilibrium state, and this is also called as population inversion condition. In general, we find more number of atoms in the ground state compared to the excited state. So here population, you can understand population is nothing but number of atoms in an energy level. Now N2 is greater than N1 is called population inversion condition. In general, we expect more number of atoms in the ground state compared to the atoms in the excited state, but now we are seeing it in reverse, inverted, more number of atoms in the excited state compared to the number of atoms in the ground state. So that is why this condition is called population inversion condition, and this state is called inverted state or non-equilibrium state. And this state exists only for a very short time. Okay, fine. Yeah. So why do we need this population inversion condition or non-equilibrium state or inverted state, which exists only for short time? Because we need this to achieve stimulated emission. In the last presentation, we have discussed about three different processes that occur when light interacts with matter. So the three processes are absorption, spontaneous emission, and stimulated emission, right? And we discussed that in spontaneous emission, the photons that are emitted are incoherent photons, and in stimulated emission, the photons that are emitted are coherent photons. And we discussed that the coherent photons are very important because when the photons are coherent, they undergo constructive interference and there will be amplification of light. So that is the reason why to get the amplification of light, we need stimulated emission where coherent photons are emitted. To get this stimulated emission, we need population inversion condition. So that is the reason why the population inversion condition is very important, because when we have this population inversion condition, only then we can achieve this stimulated emission. Yeah, that is what we have discussed. But how do we achieve this population inversion condition? Right. So in general, you don't have this population inversion condition because this is a non-equilibrium state. Always we in equilibrium state we get the N1 greater than N2, but we want this population inversion condition so that we achieve this stimulated emission. So how do we achieve this population inversion condition? Okay. So the answer is that we can achieve this population inversion condition by employing pumping techniques. Okay. So by using pumping techniques, we are going to achieve this population inversion. So what happens in these pumping techniques, or what we do in pumping techniques? We do supply energy to the system which transfer large number of atoms from lower energy level to the higher energy level. So we are going to supply energy in a pumping technique to the system. So in general, in equilibrium, all the atoms are in the ground state. By supplying the energy to the system, the atoms are going to absorb energy, and hence they are going to transfer from ground state to the excited state, because we are supplying energy in the form of light. You can supply energy in the form of light, for example. So all the atoms in the ground state are going to absorb these photons, or they are going to get excited to the higher energy level, or E2. Okay, so the lower energy level here, for example, is a ground state, and higher energy level here is a excited state, E2. Okay, yeah. So we have discussed in this slide that population inversion condition is very important to achieve stimulated emission, and this population inversion condition can be seen in inverted state or non-equilibrium state, which exists only for a short time. To understand this inverted state, we discuss what is a normal state and why do we call this as a inverted state or a non-equilibrium state. Okay. Then we discuss that, yeah, so far so good. So, but how do we achieve this population inversion condition? So to achieve this population inversion condition, we are going to use pumping techniques. And what do we mean by pumping technique? Pumping technique is nothing but supplying energy to the system in the form of light, for example, where the atoms in the ground state are going to absorb the energy and they are going to get excited from the lower energy level to the higher energy level. So we achieve, all the atoms from the ground state will go to in the next step, you will see all the atoms will be in the excited state and there will be very few atoms in the ground state. So we achieve population inversion condition. Okay. So using pumping techniques, we are going to achieve this population inversion condition, which is very important to achieve stimulated emission. Because only in stimulated emission, we will see there will be coherent photons emitted. Fine. Okay. So we have discussed what is the population inversion condition and how do we achieve this population inversion condition. And now we are going to discuss about a metastable state. And what is the question is, what is metastable state and why do we need it, right? Okay, so any atom can be excited to a higher energy level by supplying energy to it. As we discussed in the last slide, by you supplying energy to the system, you can call it as a pumping. Okay, so an atom can be excited to a higher energy level by supplying energy to it. Normally, excited atoms have very short lifetimes and they release their energy in a matter of nanoseconds through spontaneous emission. Okay, fine. What we are saying is that, okay, so why do we need metastable state? Or what is a metastable state? So to understand that, we are discussing about normal excited state. Why do we need metastable state? Because normal excited states are not good enough. Why normal excited states are not good enough? Because once the atoms are excited to the higher energy level or excited state by supplying energy to the atoms in the ground state. So in the next step, we are going to see that all the more atoms are in the excited state, very few atoms in the ground state. So we achieve population inversion condition. But before we going to achieve population inversion condition, all the atoms which are in the excited state are going to decay to the ground state in 1 nanosecond. So we are not going to achieve population inversion condition if we excite the atoms from the ground state to a normal excited state, because the lifetime of atom in the normal excited state is 1 nanosecond. Okay, so when we supply energy to the atoms in the ground state, the atoms are going to get excited to the higher energy level. If the higher energy level is a normal excited state, the lifetime of these atoms are very short in the normal excited state. They are going to decay to the ground state through spontaneous emission. And you are not going to achieve this population inversion. You will not achieve, because to achieve this, the atoms should stay in the excited state for a long time, but they are not waiting for a long time. They once we supply energy to the atoms, they are getting excited in 1 nanosecond. They are immediately going to the decaying to the ground state through spontaneous emission. You don't see this N2 greater than N1. So how do we achieve this? How do we achieve this N2 greater than N1? Even we are using pumping techniques by supplying energies, but still, because we have normal excited state, the lifetime of the atoms is very small, and immediately they are getting down to the ground state in 1 nanosecond. So still we are not able to achieve this population inversion, even we are supplying energy, which is called pumping technique. Okay, so that is the reason why to achieve this population inversion condition, we need some special state. Okay, so that special state is called metastable state, and so it means that atoms do not stay long enough at the excited state to be stimulated. Okay, as a result, even though the pumping agent continuously raises the atom, even though we are supplying energy to the system continuously, the atoms are getting excited to the energy level continuously. They undergo spontaneous emission and rapidly return to the lower energy level, which is a ground state. So you are not going to achieve this population inversion. So you need, if you want to achieve this population inversion, so you better need to have a special state as the higher energy level. So that special state is called as metastable state. Okay, so metastable state is a non-equilibrium state where the lifetime of atoms is more compared to the normal excited state. So in the normal excited state, we know that the lifetime of atom is 1 nanosecond. Okay, so population inversion cannot be established under such circumstances where you have higher energy level as normal excited state, where the lifetime of atom is 1 nanosecond. Okay, so in order to establish the condition of population inversion, the excited atoms are required to wait at the upper energy level till a large number of atoms accumulate at that level. Okay, to achieve the population inversion condition, the atoms which are excited to the higher energy level, they should wait until large number of atoms are accumulated at that higher energy level E2. Okay, such an opportunity would be provided by metastable state. Okay, so now we can define what is a metastable state. Metastable state is a, okay, so let me write down here. Metastable state is a non-equilibrium state, where or in which the lifetime of atoms is more compared to the normal excited state. Okay, yeah, so you can write down clearly. Metastable state is a non-equilibrium state in which the lifetime of atoms is more compared to the normal excited state. So this is what is a metastable state. This is a special state. It is not a normal excited state. Okay. So we are saying that in metastable state, the lifetime is more. So the atoms are going to. So now E2 is a metastable state. So I am taking this. We are going to create this. We will discuss how do we create this. But E2 is now a metastable state, and hence the atom should wait at the upper energy level E2 for longer time until there should be accumulation of more number of atoms in metastable state. Very good. Okay, in order to establish the condition of population inversion, the excited atoms are required to wait up at the upper energy level E2 till a large number of atoms accumulate at that level. Such an opportunity is provided by the metastable state, and now we have defined the metastable state is a non-equilibrium state where lifetime is more. Right now, atoms excited to a metastable state remain excited for an appreciable time, which is of the order of 10 power minus 6 to 10 power minus 8. That means 1 millisecond to 1 microsecond. Okay, so compared to the normal excited state, the lifetime is around 10 power 3 to 10 power 6 times more. Okay, so more compared to the normal excited state. In normal excited state, it is 1 nanosecond, 10 power minus 9 second. Very quickly, the atoms are going to decay to the ground state, whereas in metastable state, the atoms are going to stay for 1 millisecond to microsecond to millisecond. So 10 power minus 6 to 10 power minus 3 second. So this lifetime is more. How much more? 10 power 3 to 10 power 6 times more compared to the lifetime of the ordinary excited energy levels. Because of this lifetime, the atoms are going to, once we excite the atoms from the ground state to the higher energy level, they are going to stay for 1 millisecond to 1 microsecond to 1 millisecond, and hence N2 will be greater than N1. So we are going to achieve population inversion condition if we have the higher energy level as a metastable state. Very good. Okay. So let us see how do we create this metastable state. Very good. So metastable is fine. If you have a metastable state, you can create this population inversion condition because the lifetime is more. But how are we going to create this metastable state? So this is not be there with the system. So we need to create this metastable state. So how are we going to create the metastable state? So that is what we are going to look into now. Okay. So yeah. Okay. So how are we going to create this metastable state, which is very important to achieve this population inversion condition? So therefore, the metastable state allows accumulation of a large number of excited atoms at that level. Yeah. The metastable state population can exceed the population at a lower level and establish the condition of population inversion in the lazy medium. Yeah, so this we have discussed, right? Because the lifetime of atoms in the metastable state is more, we are going to see the accumulation of atoms in the metastable state. E2 is a metastable state now, so there will be more number of atoms compared to the ground state. So we will achieve this population inversion condition. So it would be impossible to create the state of population inversion condition without a metastable state. If you do not have a metastable state, you are not going to create this population inversion condition, because the atoms in the normal excited state will decay to the ground state through spontaneous emission, and hence you don't get this population inversion condition, because the lifetime in normal excited state is 1 nanosecond. So metastable state can be readily obtained in a system containing impurity atoms, and these levels lie in the forbidden gap of the host crystal. So we are going to create this metastable state by the presence of impurity atoms. Okay, so if there are impurity atoms, so those impurity atoms are going to provide us these metastable state, and hence we are going to create this, we are going to achieve the population inversion condition. So the important point is that how do we achieve this metastable state? By the present, or by adding the impurities, or by the presence of impurity atoms. Those impurity atoms are going to give us the metastable state. Okay. Yeah. So population inversion readily takes place as the lifetime of these energy levels are large, and secondly, there is no competition in filling these levels as they are localized level. Okay, so population inversion can be achieved if you have a metastable state, and there is no competition in filling these levels as these are localized level. So for example, transparent materials are made up of atoms with metastable state. So you can add impurity atoms, or those impurity atoms are going to provide a metastable state which can help us to achieve this population inversion condition. So there could be no population inversion, and hence no laser action if metastable state do not exist. If there is no metastable state, we are not going to we are not going to achieve this population inversion. If there is no population inversion, no laser action. So you don't see any laser that is coming out, laser beam that is coming out from the system. Okay, so to have this laser beam coming out, to have the output laser beam, we need to have population inversion. To have the population inversion, we need metastable state. So this metastable state is that much important, that will provide us this laser beam. Okay, so up to now we have discussed all the ingredients that are needed to understand this lasing action, or the process that are going to take place inside a system that will give us the resultant laser beam as a output. Okay, so this is called lasing action. Okay, so what happens in this lasing action, or how we are going to get laser beam through this system. Okay, so here figure shows the active medium enclosed in an optical resonator and being excited by a pumping agent. Okay, the resulting laser action, which is shown in figure, consists of the following steps. Right. So this is called as active medium. Okay, you have a active medium. So this one is a active medium, right? So this is written here. So this rectangle is an active medium, and we will discuss what is active medium actually. So this is active medium, and you have this this total thing is called as optical cavity. So these dashed lines, for example, so this dashed line is a optical cavity, or this is also called as optical resonator. So optical resonator, or this is also called as optical cavity. So in optical cavity or optical resonator consists of two mirrors. So you have this one is a mirror 1 and this one is mirror 2, for example. So mirror 1, mirror 2. So mirror 1, one of the mirror, for example, here mirror 1 is 100% reflecting mirror. Whatever photons that are going to come here, this mirror is going to reflect them with 100% efficiency. There is no absorption, or there is no loss of photons. In the front mirror, whereas you have partially reflecting mirror, front one is partially reflecting mirror. So basically, optical resonator or optical cavity contains two mirrors. Out of them, one is 100% reflecting, which we are always going to take at the back. Remember this one, a 100% reflecting mirror is always back, and the other one is partially reflecting mirror, which one should always be in the front. With these two mirrors, we also have a active medium in between these two mirrors, and this active medium is connected to a pump, so that we can supply energy to the active medium, so to achieve population inversion condition, and hence laser beam will come out as a output. So here from the partially reflecting, so the reason for for these mirrors, so white partially reflecting mirror in the front or white 100% reflecting mirror in the back, because we want to see the light laser beam coming out from the front, so that is why it is partially reflecting. We are not going to see any laser beam that comes out from the back, so we want whatever photons that are coming out, that are going out to the back, they should come out into the medium. So that is why we have taken 100% reflecting. So front mirror we want partially reflecting, so that some of the laser beam, so we are going to get the laser beam from the front mirror, so that is why it is partially reflecting. Very good. So laser cavity, optical resonator optical cavity is nothing but it contains two mirrors. One of them is partially reflecting and one of them is 100% reflecting, and in between these two mirrors we have an active medium. The active medium is connected to a pump, and the laser output beam is going to come out from the partially reflecting mirror. Okay. So how do we get this laser beam as output, or what are the steps that are involved in getting this laser beam as output? Okay, so there are 5 steps. Okay, so the first one is pumping. The first step that occurs in this medium is pumping. Second step is population inversion. Third step is spontaneous emission. Fourth step is amplification, and fifth step is oscillations. So these are the 5 steps that occur inside a optical cavity or the system. After the end of these 5 steps, you will see a laser beam as output. Okay, so to revise this optical resonator lasing, to understand this lasing action or to see the laser beam as output, we need to have a optical resonator, or that is also called as optical cavity. So this optical cavity contains 2 mirrors. One of them is partially reflecting and one of them is 100% reflecting. Between these 2 mirrors, you have an active medium that is connected to a pump. Okay, so you are going to get the laser beam as output from the partially reflecting mirror. And the 5 steps that are involved in the system. The first one is pumping. Okay, first we need to pump the energy to the system. Okay, pumping. Second one is population inversion. Once we supply the energy to the system, there will be population inversion, and there will be spontaneous emission, and that will give us amplification and resulting with a oscillation where you have a laser beam as output. Okay, so if you these 5 steps are very easily understood how we are going to get laser beam. First, pumping. Once we pump the energy to the system, there will be a population inversion. Once there is population inversion, we need a photon for the stimulated emission. That photon for the stimulated emission is given by spontaneous emission. And once there is stimulated emission, you have amplification, and hence you are going to get a laser beam as output. Okay, so let us understand these 5 steps one by one. Okay, so I hope you understood what is this optical cavity, and okay, we will also discuss briefly about active medium is nothing but this host material that is added. Some of the impurity atoms or defects are also added to this host material. So basically, active medium is nothing but the host material. You are going to take the host material plus impurity atoms. Impurity atoms are you can also call as defects. Impurity atoms. Impurities are impurity atoms. So active medium is made up of 2 materials. One of them is host material and impurity atoms. So these 2 together is called as active medium. Okay. It is called active medium because that is where we are going to see all these 3 steps. Okay, so you can see these all to understand these 5 steps. Here pictorially it is given. Okay, so first, the primary function of the optical resonator is to provide positive feedback of photons into the medium so that stimulated emission is sustained and the laser acts as a generator of light. Okay, so what is the importance or what is the function of this optical resonator? The primary function of this optical resonator is that this optical resonator is nothing but these 2 mirrors. So the primary function of these 2 mirrors is to provide the positive feedback of photons into the medium so that stimulated emission is sustained and the laser acts as a generator of light. Okay, so the optical resonator selects the direction in which the light is to be amplified. So the optical resonator itself will selects the direction in which light is going to get amplified, and the main function of this optical resonator, the primary function of this optical resonator is that provide positive feedback of atoms once the photons once the photons are emitted in the active medium, those photons. So here I think these two, if you consider these two are mirrors, so these mirrors are going to reflect the photons. Okay, so reflecting the photons, so that the photons are again are used in the active medium for the further stimulated emission, and that will give us the amplification of light. Okay, so we will discuss the lasing action in detail in the next presentation.
Like, share and subscribe. Hit the bell icon for more updates.